Between the poles of the powerful magnet is a cylindrical uniform magnetic field with the diameter of that and the strength of that. The wire carries current through the center of the field at an angle of 65 degrees to the magnetic field lines. If the wire is, what is the current flowing in it? Okay. So just kind of on a random side note before we jump into the problem, we said if you have a magnetic field going in a straight line, then particles want to move in circles around it, right? Well, what if you want things to go in a straight line? Well, it winds up being really simple. If you build the magnetic field going in a circle, then things will go in straight lines. So that's so if we have a cylindrical uniform magnetic field, then yeah, there you go. The diameter of that, strength of that, a wire carries a current to the center at an angle of that to the magnetic field lines. That's the wire. Experiences the magnetic force of that. What is the current flowing in it? So I'm sitting here thinking, do I need to know the diameter of the magnetic field? I feel like I should just need to know the strength of it. Oh yeah, I do need to know the diameter of it. Thanks. Let me guess right quick and make sure that this works. So if I go 3.8 centimeters, so that's 0.038 times I. That's the circumference of one loop times 1.2 for the strength of the field times sine of 65. So force should be equal to that times current. So if they give me the force, I just need to do force divided by that guy. So 1 over x times 0.05. So let's try that. 0.404 amps. Nope, that's not right. Okay. I'm sure they work out this sort of scenario in the book, but I don't really want to look it up right now. Okay, that's weird. Okay, I'm going to look in the book just because I have a hard time believing that. So the reason I think that's weird, so they did two things different than we did. Yeah, I can go back and get it. Oops. Oops. So I did pi times d for the circumference instead of just d. But so that was one difference. And so that one doesn't really surprise me. What does surprise me, though, is that the 65 apparently doesn't matter at all. Which is strange. So I'm going to, and like I said, I'm sure they actually work this out, this scenario out in the book. And they're just wanting you to use the answer they got there. I'm going to look it up just to double check. Okay, what? What was the, yeah, the 1.2 is the B. And again, they have somehow made this thing freaking huge. I was hoping that I somehow made this huge whenever we were doing this the other day. I was hoping it would get smaller again. Okay, that looks better. All right, 20. Motion of charged particles, force and torque. And force on a current carrying conductor. Yeah, I think that's where we're. Maybe they don't work this one out. Yeah, I mean, it's really simple. I guess it's just a, and as far as actually getting the answer, it's simple. It's just trying to understand why that's the answer is trickier than some would think. I guess what's going on is, I mean, this wire is going in a circle. There's, oh well. Are you happy enough just knowing what the answer is and not totally understanding why that's the answer? Yeah. Okay. Sorry about that. Let's see, what time is it? Yeah, we probably got time for one more. So let's do one more. Let's do the last one. We'll call that good. It has 4 parts. We'll declare victory over homework 5. We'll tell Colby that he was sad for not being here today. And that is oriented with this. Okay, so just one quick thing. What this book uses for in and out, it's supposed to be like you're supposed to imagine an arrow. So it's like the X or whatever is like the feathers on the back end of an arrow. So if you see X's like that, that says that the field is going into the board. And if you see circles, oh, that's like the tip of the arrow is flying at you. So that means you've got a magnetic field coming out of the board. Okay, calculate the net magnetic force that this field exerts on the coil. Okay. With this, they do work out in the book we just closed a second ago. It's still actually up. If you think about force, it's actually pretty easy because you think, okay, well, you can let's right hand roll it right quick. Let's do it on this right hand part right here. Okay, I've got this is my current, my field is into the board. So right hand on my palm facing towards the force on this guy is going to be that way. This on the other one is opposite, right? Because everything's the same except the current's in the opposite direction. So on one hand it's pushing it to the left, on the other hand to the right, so they're going to cancel. Same thing on top and bottom. So if I look at the force on this thing, I'm going to get 0. And now my calculate the torque. Let me try right hand rule this thing again. Right hand rules can be hard. So put my hand there. That forces that way. That forces that way. If I do it on the top and bottom, if I put my hand on the top, down, up, the torque is also 0 in this case. Yeah. Because again, the right is being pushed left, the left is being pushed right, the top is being pushed down. So it's not twisting or anything. Right? What's going to change is here in this next one, about the axis, calculate the force. So the force is still going to be 0. In the grand scheme of things, everything's going to cancel out. What's not going to be 0 is the torque. So if I take this whole thing and I rotate it 30 degrees about the axis, the left side coming out of the plane, the right going in. So now I've kind of tilted it. This thing is slightly out, this side is slightly in. The force on the bottom is still that way, the force on the top is that way. So this whole thing is going to twist. Right? Does that make any sense? Or okay. Yeah, it's hard to do three-dimensional stuff. Okay, it's like, as it is sitting in the plane, this is being pushed to the right, that one's being pushed to the left. So, I mean, nothing's happening. But if I raise this up and lower this one down, when I push this to the right and that one to the left, it means it's like this whole plate is spinning. Okay. So that's what we want to do, is find the torque on that's making it spin. All right. And since we're nearly out of time, let me go back to the book, because that was the next section in the book, since they compute it for us. So the total force is, okay, the current, the torque is the current, A is the area of the loop. Actually, let me make it a little bigger for you writing it down. Okay, you think you got it? Yeah. Yeah, A, B, sin theta. So again, I is the current, A is the area of the loop, B is the magnetic field, theta is the angle between the magnetic field and the normal vectors of the loop. So, where's the problem? There's the problem. Okay. So the current is 1.9 times the area, which is 0.22 times 0.35, times the magnetic field is 1.4. And now and then times the angle, which the way they worded it, it really is just 30 degrees. Sometimes you have to think about it. Wanted to make sure it wasn't 60. I don't think it's 60. Yeah. So again, the angle is between the magnetic field and the normal vector, so for this one, the normal vector is straight out of the page, the way it's sitting there, it's the other right-hand rule. So which we'll talk about later, like if you have a current or whatever, it makes a magnetic field. To find the magnetic field, you put your right hand going around like the current is. So my fingers are going in the same direction as the current, and it's the way my thumb goes. So when it's just sitting there, the normal vector is straight out. The field is straight in. So sine of 180 is 0. So that's why we got 0 for the torque right there. And now if I twist this at 30 degrees, now the normal vector is over here. It makes, I guess, a 150 degree angle with sine of 150, which is a half. Cool. Yeah, it's kind of weird.